I'm making a drawing in 3 dimensions. So I'll do it this way. Going up is the expense, which is this volume, divided by this volume unit. Anyway, I know what it is. It's EP delta slash SMA squared. And on this vertical line of bad news, the higher you go, the more expensive. There are several measures of interest. One is called, meaning ticks. One is 12, the other one is 6. We showed a number called 4, and then 2, and 0, certainly. And so at this location is the design, the beginning of the story, which was untouched by our imagination, the solid rod that was called design number 1. Let's call it 1. And then what I'm sketching is a two-dimensional design space. The design space is in the base, a population of designs that multiplies because of changes in the architecture. And going in this direction is tapering. And this other direction is hollowing. In the first book that I wrote with these ideas in the year 2000, I called tapering shape, and the other one structure. Okay, so I can forget about tapering, shape, and structure. And if you have shape, then clearly the performance is 4. And this design that had 4 was called design number 3. Sits here. If the design has only structure, meaning the hollow tube, then its performance is with 6 units, and that design number 2 sits here. So now you're getting 3 points in space. The original one and these babies of having changed the design in only one direction at a time. And then finally, this number 4 is the result of either taking the tapered and making it hollow, or taking the hollow and tapering it. And the place of this design is here in the outfield to a height of 2. So that's design number 4 according to today's lecture. Now squint and try to overlook the lines of the construction, and remember only these 4 points in space. Now if you squint even harder, you'll be able to imagine a surface that looks like an apron, something like this. A surface that is like the slope on a hill covered by snow. That suggests that maybe. If you fall down enough into the valley on your skis, you'll fall down to an altitude even smaller than 2. You see here, it is good to know that by endowing the drawing with more degrees of freedom, eventually you reap benefits in performance. Well, it is even more important not to stop. Maybe there is value in aiming for the moon in the way you shoot, and ask, after having distributed the stresses uniformly in this object, can we do better? Do you see any more material that's lazy in this tube, like the top of the big pen? A tube in bending? Let's find out. So you look in the cross section. So key question: can we do better? Better than a volume with only 2 volume units. If you look at the cross section of the hollow tube that's tapered, we see obviously the North Pole and the South Pole here. With these 2 fibers, dorsal and ventral at SMA. But those are the only fibers that are suffering or the first to break. Famous for their laziness are the fibers in the vicinity of the equator. So this is the so-called neutral plane. The beam is bending in a vertical direction. Then the rest of this donut, except for the top fiber and the bottom fiber, is suspect. And I would say it deserves to be eliminated. You see? So the next step is to eliminate those orange parts. Well, here's the next drawing, in which we have only the top fiber and the bottom fiber. I'll draw them this way because you expect these fibers to become narrower as they reach the tip, but that's not the point. The point is that if you take a wire, and you bend it this way, well, and you load the wire at the tip, it will be a weak beam. A wire is as strong as the wire as a rod, a thin and long rod, small cross section, which is the way this whole story began. A coat hanger is not that stiff, you see. No, and the reason is that I'll make it even bigger. If this is your object made of only 2 fibers, the top one and the bottom one, then when you bend it, the shape becomes limp. And in mechanics, this feature of weakness, because the top fiber bends independently of the bottom fiber, it is known as the fact that these so-called, if initially these 2 places belong to one cross section when the beam was not loaded. When the beam was bent, these two places. Let me put it another way. Imagine a plate with this shape. When the plate is deformed to go, say, down here, then the so-called cross-section drawn this way in the original shape simply rotates as a plane to its new position, the position of the cross-section in the bent beam. So when the object is solid, pure bending means that plane cross-sections remain plane as the beam is bent. That is not happening when the upper and the bottom fibers are bending independently. So the reason why the so-called chainsaw design is a stiff one, stiff enough for you to cut a tree log, is that yes, it has a top fiber and a bottom fiber, that is the chain that goes around and does the cutting, but the stiff design also has a plate here that connects solidly the top fiber to the bottom fiber. That plate is called web. So the correct drawing is one that has these two fibers, but those fibers are rigidly connected with a thin plate, a web, that forces those fibers to bend together, meaning that the cross-section at any x is that of the top fiber and the bottom fiber connected by a plate called web, which in the next part of the analysis will be assumed massless. So this is thin, and therefore it will be neglected when it comes to the material. And then this is the top fiber. It will be a cross-sectional area corresponding to this location here at x. And the height of the web will be called h of x. And this is how, in the minds of the inventors now, from probably much earlier than the Industrial Revolution, people figured out the usefulness of beams with I profile. The letter I is here. It comes from this idea that the hardest working material is the one that's farthest from the neutral plane, but those stressed fibers must be connected together rigidly to avoid this kind of mistake. You see that? So I beam profile will be the topic that brings us together right after the spring break.